Docker. It's one of those technologies that, let's be honest, feels a little bit like magic. We package up our applications, ship them off in these neat little boxes called containers, and they just work everywhere. But have you ever really stopped and wondered what's happening under the hood? How is this not just another virtual machine? Well, that's what we're going to break down.
This, right here, is the big question. It's the central engineering puzzle that Docker solves. How do you get that perfect, pristine isolation for every single app without the insane overhead of traditional virtualization? Well, I'll tell you right now, the answer isn't magic. It's actually just some incredibly clever engineering that's built right into the core of Linux. And together, we're going to unpack it, piece by piece.
You know, to really get why Docker is such a big deal, you have to remember the absolute pain of the world before it. I mean, if you've ever worked in software, you know this slide in your bones. You'd have one project that needed an ancient version of a library and another that needed the brand new one on the same machine. That's dependency hell. And of course, your laptop was totally different from the server, which gave us the most infamous phrase in all of tech. Well, it works on my machine. For a long time, the fix was virtual machines, but that meant spinning up an entire separate operating system for every single application. It was just so slow, bloated, and incredibly expensive.
Okay, now this slide really gets to the heart of it. This shows you the fundamental difference. Just look at the stack on the left, the virtual machine. You've got your hardware, your main OS, and then this thing called a hypervisor. Its job is to create a complete simulation of another computer. On top of that fake hardware, you have to install a full guest operating system, like a whole new copy of Windows or Linux, just to run your app. Now, look at the right. See how much cleaner that is? The containerized app sits way closer to the metal. There's no guest OS. There's no hypervisor. It talks to the Docker engine, which then talks directly to the one host operating system kernel that's already there.
This right here, this is the secret sauce. This is the key to everything. All those containers running on your machine, they are all sharing the exact same Linux kernel that your host machine is already running. That is what makes them so unbelievably lightweight and fast. They aren't faking the hardware like a VM. They're essentially just borrowing the running operating system.
And that leads us to probably the biggest aha moment you'll have when you're learning this stuff. A container is not a tiny computer. It's not a mini VM. At the end of the day, a Docker container is just a process. A regular old Linux process, just like your web browser or a command line tool. The only thing that's special about it is that it's been launched with a very clever set of rules that trick it into thinking it's completely alone on the system.
Exactly. That's the next logical question, right? If it's just a process, how on earth does it get its own private file system, its own network? How can it be blind to all the other processes that are running on the exact same machine? Well, the answer comes down to two extremely powerful, and actually pretty old, features that are baked right into the Linux kernel itself.
So the first piece of this engineering puzzle is a feature called namespaces. The best way to think about a namespace is like a bubble of isolation. When you start a process and tell the kernel to put it inside a new set of namespaces, you're essentially giving that process its own private, customized view of the world. It's like putting blinders on it so it can only see the resources that are inside its own little bubble.
Now, Docker uses a whole bunch of these namespaces to build that bubble. The PID namespace, for instance, gives the container its own private list of processes. Inside, your app might think it's process ID number 1, the first and only process in the world. The network namespace gives it a brand new virtual network card with its own IP address. The mount namespace gives it a completely separate file system tree so it can't see the host's files. And the user namespace is really clever. It lets a process think it's the all-powerful root user inside the container, while on the actual host machine, it's just a regular low-privileged user.
And this table shows that PID namespace in action perfectly. Look on the left, inside the container. Our app starts a process called watch, and it sees it as PID 79. Simple enough. But now look at the host machine's point of view on the right. The Linux kernel sees that exact same process as PID 12675. The namespace is just acting as a translation layer. The container gets its own little world, but the host always knows the real story.
Okay, so isolation is fantastic. But what's to stop one container from going crazy and chewing up 100% of the CPU, starving every other process on the machine? That's where the second key piece of technology comes in, control groups, or Cgroups. So if you think of namespaces as building the walls of the container's private room, Cgroups are the ones that set the utility limits for that room. They dictate how much electricity, or CPU, and how much water, or memory, that container is allowed to use.
All right, we've got isolation, we've got resource limits, but what about the files themselves? How are Docker images so incredibly efficient and fast to download and share? The secret here is a really cool file system trick called a union file system. Instead of being one huge single thing, Docker images are built in layers, kind of like a stack of transparent sheets. So let's see how that stack works. You start with a base layer, which is read-only. Think of it as a tiny minimal version of Linux. Then you add another read-only layer on top that installs your dependencies, like Node.js. Then another layer on top of that with your actual application code. All of these layers are locked, they can't be changed. But here's the magic. When you actually run the container, Docker slaps one final super thin, writable layer right on the very top. If your app needs to change a file, that file gets copied from a lower, read-only layer up into this writable layer, and then it's modified. This copy-on-write system means you can have hundreds of containers all sharing the same base layers, saving a ridiculous amount of disk space. So, let's put it all together. When you type that simple Docker run command, this is the chain of events that kicks off behind the scenes. First, Docker's storage driver assembles that layered file system. Second, it makes a call to the Linux kernel and says, "Hey, give me a new set of namespaces." Third, it configures the Cgroups for that new process to set its resource limits. And finally, with all of that in place, it launches your application's process inside that brand new, perfectly isolated and resource-limited environment. And the result of all of this beautiful, low-level engineering? Sheer, unadulterated speed. Because we are not booting an entire operating system from scratch, a container can fire up in less than a second. We're just starting a process, not booting a computer. Now compare that to the minutes, literally minutes, it can take for a full-blown virtual machine to get going. It is an absolute game changer. In this architecture, it's not just a neat technical trick. It is the engine that powers so much of modern software development. It's what makes microservices a practical reality, letting you run lots of small, independent services that can't mess with each other. It allows for crazy fast scaling because you can launch new copies in a heartbeat. And because the container bundles everything together, it is the ultimate cure for the works on my machine plague. It guarantees that an app will run the exact same way on your laptop as it does in the cloud.
So if you remember just one thing from all of this, let it be this. Docker's magic is really just a masterful orchestration of powerful features that have been sitting in the Linux kernel for a very long time. It isn't building tiny virtual machines. It is simply taking a normal process and expertly wrapping it in namespaces for isolation, Cgroups for resource control, and a union file system for incredible efficiency.
It's really just such an elegant solution to a very messy and complex problem. By understanding these core building blocks, namespaces, Cgroups, layers, you've basically peeled back the curtain and seen the real machinery at work. So the magic is gone, but it's been replaced by something better, a genuine appreciation for the clever engineering that makes it all possible. So now that you know how it really works, what are you going to build with it?